So the multiple choice is still open for those of y'all that were out yesterday. So make sure you get in and do the multiple choice. Today we're going to do the exploration. So if you click on the reading, it will take you to the first page of the reading. Click on explore more resources. And when that pulls up, if it does, go all the way to the bottom of the page and click on the exploration. This is the exploration for earthquake impact. So here we go. Let's take a look at the exploration itself and see what we can do here.
I thought he was moving the board.
Let's see. All right, so we got the exploration pulled up. They give us a couple instructions, which obviously we're just going to skim through. And then they have a couple different sensor machines. So what they're trying to do is sense an earthquake or a tsunami before it happens. So we've got an early warning station up here on land. We've got a buoy out in the ocean. We have a satellite up in space in orbit. And we have an underwater pressure sensor down on the ocean floor. And so each of these are going to try to observe when the conditions are right for a tsunami to form. And so I believe, let's see, if we click on, we're not clicking on anything here. Go to explore. All right, so go to explore. So the apparatus tab just explains about the different apparatuses. It doesn't look like there's anything. You can really click on what?
What is that? Underwater pressure.
Underwater pressure sensor. So again, it's just showing you what the actual sensors look like and kind of describing them a little bit over here. So if you go to the Explore tab, they will give you a couple things to do. It looks like what we're going to do is trigger an earthquake or a volcanic eruption or a submarine landslide and see how these things kind of get picked up and relayed back. So let's leave it on earthquake. Let's click trigger. And what's going to happen is our earthquake happens. It sends a pressure wave to our receivers here. And it looks like they're going to communicate with the satellite and then maybe back to the ground station. So let's do this one more time. So we trigger the earthquake. Yeah, and you can see the pressure wave goes to the sensors. The sensors communicate with each other and the satellite beams that signal down to the recording station or the early warning station. Is there anything else for us to do here? Proceed. So they're doing this some more. We can issue a tsunami warning. So issue a tsunami warning. If you're in a boat but far out at sea, stay out there. So that's smart because the boats that come in are going to get caught in the waves, whether when it's coming in or the wave that goes back out, and that's going to be a lot of problems. So being out at sea is actually the best place for you to be if you're a boat. The closer you are to shore, the more dangerous it is for you. So the rest of the options, it looks like, were not good advice. It's okay to return to the beach after the first wave retreats. That's not true. There could be secondary waves. There could be other problems happening. Take some time to investigate the bare seafloor as the water recedes into the ocean. No, that's the pullback thing that we talked about. You want to stay away from the pullback because you know the wave is coming. And then do not return to the beach for at least one day. You want to make sure that it's completely safe. It's not like a timed thing. So just be aware of that. So let's see, what else is there to do? They record some more data here. You can see now the tsunami's coming onto land. So it's coming up. What are our options here now? I guess that's it. So nice. All right, so now I guess we can reset or we can plot it. Drag the selected parts of the graph to expand on the x-axis. What are we plotting? Pressure here and time. What is the maximum time taken for the pressure to drop from peak to low? So here's your peak pressure. Here's your low pressure. And so from peak to low, we're looking at what? This is time in hours, so this is maybe what, 6 hours? 6 to 12, 24. So this would be what? 24 minus 6 would be 18 hours, I guess. Although that doesn't look right. What are they saying here? Let's look at this one. This one would be 8 hours to 16 hours, so roughly 8 hours. Let's try the 9.5 one. I think that's good. Enter the approximate arrival time of tsunamis using pressure variations recorded. So this, we're looking for tsunami times. So I guess your tsunami is going to be what? 1445 and 1500 hours. Right in here. 13, 9, 12, 9. Yeah, I don't know. Between what? 12 and 15? 12 and 15? I don't know where they're getting that from, but.
It's like all the spikes towards the middle.
Yeah, I guess that would be the tsunami right there where you have the high up and down. Those are the actual waves coming in. Okay, that makes sense. And if the velocity of the tsunami wave is 840 kilometers per hour, at what time will the first tsunami wave arrive at the coast, which is 140 kilometers away from the underwater pressure sensor? Okay, so that's when the tsunami reached the underwater pressure sensor. Then how long will it take to get to the coast? It's 840 miles per hour, and you want to go, or kilometers per hour, and you want to go 140 kilometers. That's going to be pretty short there. So I'm going to imagine the 1300 one. No, the 12 one. So it's going to reach there pretty quickly. I don't remember the original time, so not bad. All right, I think that's about it. Let's see. I guess the other one is going to do the same thing. Trigger volcanic eruption. We're pretty much going to get the same stuff that happens. Proceed. Issue a warning. Yeah, move as far away from the beach as possible. I'm going to get down here. I don't know why that keeps resetting things. What do we have to do? Oh, there it goes. Plot it. All right, so let's move on. Let's get to the questions and see if we can answer the questions. What do we have? 10 questions. Don't worry about question number 11 over here on impacts 2. Is it just one question? Of course it is. Nope, 2. 3 of them this time. But still, we're just going to do 1 through 10. And let's take a look at the questions. So, question number 1. Describe 2 causes of tsunamis. How do these events cause tsunamis? So, the easy way is obviously going to be earthquakes. And you can say underwater volcanoes, underwater landslides. Basically, the way that they cause tsunamis, what makes an earthquake cause a tsunami is going to be the change in the seafloor. So if anything changes the level of the seafloor, either pushes land up or pulls land down, and I get the bottom of the ocean moving up or down, that's going to be what creates a tsunami. And so an earthquake is obviously going to do that. A volcanic eruption underwater will do that, or a landslide underwater. All of those are going to change what level the seafloor is at, and so they will cause a tsunami. So number 1, just give one of those 3 earthquakes, underwater volcanoes, or landslides, and make sure you point out that the change in the seafloor elevation or the height of the seafloor is what causes tsunami. Number 2, describe the primary and secondary cause of destruction during a tsunami. What's going to be the primary cause of destruction during a tsunami? Yeah, the wave itself, like the direct impact of the water, that's going to be your primary cause of destruction during tsunami. So the secondary cause, some of the secondary causes of destruction, let's see what they go through here. Draw down along the coastline. Here you go. Tsunami destruction. So they got warning signs. Well, yeah. So I'm gonna say the flooding. Is that going to be primary or secondary? I would say flooding could probably be primary because that's part of the initial wave coming in. It's not just the force of the wave knocking things down, but the flooding itself. So secondary causes of destruction of tsunamis are going to be knocking out of vital services. So your electricity's out, your gas is out. Usually your hospitals are going to be down. The roads are closed. So those are going to be a lot of problems just for handling normal everyday stuff. I guess flooding could be one. Trying to think of some other things. I think those are going to be your main side kind of results are power going down, water contamination, and sewage contamination are going to be a big deal.
Gas?
Yeah, any gas lines that are underground are going to be affected. And so pretty much anything that we bury underground or we kind of use and rely on every day, like water, electricity, working roads and hospitals are going to be affected. So I would just go through those and that should be fine. Although it'd be nice if they kind of had a list here. Stuff that they were looking for. So they talk about inundation, all the different waves. Yeah, that'll be fine.
Mr. Bailey,
What's up?
can I go to the bathroom?
Yeah, I guess we quit. I mean, we are like right in the middle of something, but
Oh, wait.
yeah,
You should
that's
wait.
probably a good idea. Okay, so let's see. Question number 3. Explain why it is incorrect to refer to tsunamis as tidal waves. Tsunamis don't have anything to do with the tides. They can come at any point during any tide. Tidal waves are caused by gravity. Gravity is not the cause of tsunami waves. So I would just say that tidal waves or tsunami waves are not associated with tidal waves. They're not caused by gravity, and they're not the same thing.
I didn't correct.
What? Number 3? Yeah, that's number 3. So why is it incorrect to refer to tsunamis as tidal waves? Because they're not caused by gravity like tidal waves are. Tides are caused by gravity from the sun and the moon. Tsunamis are not caused by gravity. So, number 4, explain how underwater pressure sensor located miles away from the coast can help in issuing tsunami warnings. So obviously this makes sense because the wave is coming from the ocean towards the shore. If I want an early warning system, I need it to be out in the ocean. If my warning system is on the shore, it's not going to know that the wave is coming until it's already here. That's not a very good warning system. And so you need your locator to be out in the ocean. So the idea here is the sensor out miles away from the shore will detect the tsunami wave before it gets to the shore and send a warning signal so that people can evacuate and prepare before the wave gets there instead of after. So that's how your underwater pressure sensor located miles away from the coast can help issue warnings, is it senses the wave before it gets to the coast, before it gets to the beach, and sends out a warning that a wave is coming.
Do you think there's ever been like where there's people on the ocean and it just happens?
What, like a tsunami?
Yeah.
Oh yeah. I mean, we talked about that movie there, that the Impossible movie about the tsunami in Indonesia. There were thousands and thousands of people on the beach when that happened. Now, out in the ocean, you could be out there, but it's less dangerous for you because the wave doesn't get very big until right when it gets in the beach. So if you're out in the ocean, you're going to experience like a little bit of a wave, but it's not really enough to capsize boats or cause very much danger. And so actually being out in the ocean when a tsunami happens is kind of one of the best places to be.
I think you said it goes like 300 miles an hour.
It does, but the wave's not very big. So it travels fast through the ocean, but it's not really above the surface. So your boat's not really going to notice it. Now, the downside to that is if you're on a boat, at some point in time, you have to come back to harbor and get back on land. And if you're out to sea when a tsunami hits, the tsunami is likely going to take out all of the like piers and docks and ports and all the stuff that you would actually come back to. And so might be a little bit of adventure coming home, but you'll be safer on the boat out in the ocean when the tsunami actually happens.
At least you have your boat, like everybody else.
Yeah, and that's one of the things, like if there is a tsunami warning, I don't know that this is advisable and this is something that you should do. But yeah, if you have a boat and it's like your livelihood, you might get in your boat and go out to sea and try to get further out before the tsunami actually comes, and it could save your boat. Now, the problem is, if you don't make it before the tsunami comes, you've like sacrificed all your safety and now you're in a bad spot. So I don't think they're advising anybody to do that, but there's probably are people that do that when the tsunami warning comes. Yeah.
So whenever you're in a boat, what if you're behind the tsunami instead of in front of it? Can't you just go back, like follow it, whatever?
You could, but it moves really fast. It's going like hundreds of kilometers per hour, so your boat's not going to be able to keep up with it. But yeah, you can kind of follow it in a little bit, but you don't want to get too close because when it goes up shore, it's going to come back out and it's going to bring all that junk that it knocked off with it, and so you don't want to have your boat up close to shore and then everything's coming back out to sea. So in general, you just try to stay away from it. So number 5, compare and contrast tsunami and sea surface wave. Did I get that right? Yeah. So compare and contrast tsunami and sea surface waves. Sea surface waves. There's not a lot to compare and contrast here. So basically, as far as how they look on the surface, they're going to look very similar. Your tsunami isn't going to look any bigger or different than a sea surface wave. The only difference that is going to happen is the speed. Your tsunami wave, like we said, is going to be traveling very, very fast, hundreds of kilometers an hour, where your sea surface waves just travel at a normal speed, maybe a couple kilometers per hour, a couple miles per hour. However fast the wind is blowing is usually a good indication of your surface waves. And so visually, they're not going to look any different. But speed-wise, the tsunami wave will be traveling much faster than the actual surface wave. So visually the same, speed, the tsunami wave is traveling much faster. Number 6, explain why boats far out to sea are unable to notice the tsunami wave. That's the same thing. We've kind of been talking about this. The tsunami wave's not very big out at sea. And so it just looks and feels like any other wave. You have to have very sensitive equipment to notice how fast it goes by you. And so unless you're looking for it or you have some sort of sensor on your boat, it's just going to go by like any other wave and you're not going to notice it. So that's why boats far out to sea are unable to notice the tsunami, because it looks and feels like any other wave. And you would not notice it. Number 7, why are tsunamis more common in the Pacific Ocean than in the Atlantic Ocean? Any guesses to this? Why do they happen in the Pacific Ocean all the time but not the Atlantic? Yeah, more earthquakes. That's it. Pacific Ocean has all the earthquakes. Not all of them, but they have most of them. The Atlantic Ocean has almost no earthquakes, almost no volcanoes. The Atlantic Ocean is pretty calm. So they don't really get tsunamis in the Atlantic Ocean. They're very rare. So why are they more common in the Pacific Ocean than the Atlantic Ocean? Pacific Ocean gets way more earthquakes, way more volcanoes, and way more plate tectonics. The Atlantic Ocean basically has none of that. So number 8, tsunami is a hazard associated with an earthquake. Describe some other hazards associated with earthquakes. So other hazards associated with earthquakes, they kind of went through this. Obviously, the initial earthquake itself, so the seismic waves, the shaking, that's going to be a hazard in an earthquake. I mentioned that fires and floods are often hazards associated with earthquakes because, well, that didn't change over. Because we bury our electrical lines and our power lines underground. And so often when you have an earthquake, you get flooding, you get fires, you get power outages because of that. What else is a problem with earthquakes? Landslides could be a thing. We already talked about fires and floods. None of the weather stuff. I think that's pretty good. So landslides, power outages, fires, floods. They already mentioned tsunamis. That should be good. Those are other hazards associated with an earthquake. Number 9. Oh, wrong one. An earthquake triggered in the Pacific Ocean at 17:21 p.m. Calculate the arrival time of the tsunami at the coast, which is 406 kilometers away from the epicenter. Assume that the velocity of the tsunami wave is 840 kilometers per hour. And so this one is a quick little math problem. Do it on your own. It's not too bad. They give you a speed, 840 kilometers per hour. They give you a distance, 400 kilometers away. So you should be able to, what are you doing with this? You should be able to divide these and get a time. So when you divide these, you should get a time in hours of how long it took for that wave to travel that 406 miles. Then you take that time and you add it on to the time that the earthquake actually happened. So if it takes, let's say, half an hour for it to travel that 406 miles, you want to add on a half an hour to 17:21 p.m. and tell me what time the earthquake actually arrives there where they're mentioning. So just divide and then add, and you should be good.
When you divide by 840 by 1721, it is 17.
No, the time is what you're going to add to. You're going to divide, I'm not going to tell you which one because you should be able to figure it out. You're going to divide the 406 kilometers with the 840 kilometers per hour. And if you do it the right way and put the right number on top, you're going to get a certain number of hours that this worked. And I'll tell you, if I can go 840 kilometers in 1 hour, how long is it going to take me to go 406 kilometers? It's going to be less than an hour, right? Because if it was a whole hour, I would have gone 840 kilometers. So whatever way you divide it, it should be point something. It should be less than 1. That should be your number of hours. So you need to take that, figure out how many minutes that is. Because if I have like 0.4 hours, that's not like 40 minutes or something like that. You got to figure out how much that decimal is in minutes, add those minutes to your time, and give me a time. And know that if you're wrong on your time, people die. Real people in real life. No. But seriously, you want to be right on your time. If you're 5 minutes late, and this is your real job, for real, people die because the wave got there 5 minutes earlier than you told them it would. You got to do your math right. So, number 10. In some cases, people observe the sea rushing away from the coast before the tsunami wave floods the land. Why would this happen? I was going to say I feel like y'all already answered this, but I think I'm getting y'all confused with my dual credit class. So we did talk about this, though. Why does the ocean pull away from the land? Why would this happen? If you want a little bit more detail, it's on the tsunami page. But basically, as the wave comes up towards the shore, there's a little bit of that pullback. Let's see if they describe it here. As the water from the beach like feeds the wave. It's the best way to kind of put it. So, a tsunami, a series of waves, shallow water wave, blah, blah, blah. They don't talk about the pullback here. A deadly wave. Here, I think they talk about the pullback. They describe the run-up. They describe the time the wave comes. The drawdown. Here you go. So, the drawdown they talk about in this chapter, the drawdown describes a scenario where the wave trough hits the shoreline before the crest. When this happens, the sea level appears to drop rapidly, which results in an even more sinister event because it looks like the water has gone away and then it comes in. Do they have video of this? No, that's a tsunami. I'm breaking around the palm trees. Okay. So yeah, it's the wave comes in, and basically the point is with any wave, like if I have a wave that comes up, I'm going to have a trough on the other side that's low. And so if this is coming in towards the shore and it just times up right where my trough comes ashore before my peak does, I will see the water kind of go down before it comes up for the wave. That's that pullback event. So that's how they kind of describe it there in that paragraph. So that was question number 10, right? When you get done, make sure you hit submit. I'll go in and get them graded. If you have any questions, want me to go over one of them, let me know and I'll do it right now. And for those of you that were absent yesterday, go in and do the multiple choice assignment and get a grade in for that. Everybody good? Nice. So I will post this online for the people that are absent. And yes. So basically, that's part of the pullback is when the wave approaches. If the trough, and that's how they're describing it here. When the wave trough hits the shoreline before the crest does, basically it looks like the water goes away first and then the wave comes. And so that's what they're talking about with they call it drawdown. I've heard it called pullback. So that's kind of their explanation for it, which is a fairly good explanation. So let me stop this.